This conference will now be recorded. This conference will now be recorded.
Hello students, today we are starting discussions on the POIQs from JEE Mains 2nd September 2020 paper. So let us start our discussions. So this problem, first problem says a train A and B are running on parallel tracks in opposite directions with speeds 36 km per hour and 72 km per hour respectively. A person is walking in train excuse me in train A in the direction opposite to its motion with a speed of 1.8 km per hour. So this is actually a problem of relative motion. Look, you have to find out if a person walking in train A in the direction opposite to its motion with speed 1.8 km per hour. Speed in meter per second of this person observed from train B with B will be close to what out of these four options. So look what happens when there is a person over here. Let's say this is B. Okay, this is B. So it is moving in this direction, say with this kilometer per hour. So if I just write this as BB and I want to write in terms of meter per second, then see VB, see I have to just multiply 5 by 18. Okay, so this is ultimately becoming 20 meter per second. This will be meter per second. So VB I am directly writing VB is 20 meter per second. Okay, so guy B is see there is a person B which is sitting in the train B which is running with this speed. Another train A, let us say this train is moving in the opposite direction, so I am just taking this way, and VA is how much? 36. So half of this 36 kilometer means half of this speed, so this will be 10 meter per second. 10 meter per second. Okay, so this is the train A. But see, a person in train A is again just moving, walking. Say this person is walking walking. Okay, so with speed 1.8 kilometer, so the speed of this person is 1.8 kilometer per hour. So if I multiply this with this, then it will give me 0.5 meter per second. Okay, so this is all right. And this guy, say a person is walking in train in the direction opposite to its motion. The person is actually sitting or inside in the train A. The train is moving in this direction, in the leftward direction, as you see here. But the person is walking. Let me give this hand this way. Okay, so it means the person is walking in this direction, and what is the speed? 5 meter per second. That means, this man has a relative velocity with respect to its frame itself. So its frame is the train A, and it has a relative velocity. Ultimately it is moving with the train itself. Okay, even though he is walking in the opposite direction of the train A, but he is ultimately moving along with the train itself, but with a lesser speed than this train, because it is moving in this direction. Train is taking him with certain velocity, but it will actually experience see net velocity in this direction along along the direction of speed of train with this much. Let me tell you. So it is the speed of the person with respect to the train, or yeah, so this will be 10 minus 0.5 meter per second. I hope you are understanding this, because the man is walking in the opposite direction while he is in the train itself. So this will be like this. Now this person in the person sitting in the train B will look this guy, and what will be the relative speed of this guy with respect to this. Now I see this, actually this is the speed of the person with respect to the train, and this guy, now I see relative speed. How do you find out when they are moving in the opposite direction? You have to just add it. Okay, so if two objects are moving in the same direction with different speed, then I have to, suppose this is VA and this is VB, I have to actually take relative velocity VA minus VB. Okay, so relative velocity, since both are moving in the opposite direction, suppose if I write VA minus VB, or VB minus VPA PA, then then actually I have to find out the relative velocity of the person with respect to B. Okay, let me write it here itself. So VPA person with respect to B. So I have to write VPA minus VB. See, if I just consider the direction, so this is actually, see, 9.5. Now they are not in the same direction. In the opposite direction, I have to write it here 20. This is meter per second. So it will give you 29.5 meter per second. Okay, so this is actually the answer. Okay, I have messed it like writing every like here, but it is the way to do. Okay, so this is the procedure you have to follow. So that, okay, so you get the answer D here. So here you should not think that since the person is inside the train and whatever speed he may walk with, its speed is same as the train. This is actually the clue here. Okay, so where you will do the mistake, you will take the speed of this guy as 10 meter per second itself. It is not actually. Okay, so you have to find out the speed of this person with respect to the train. Okay, as he is walking in the opposite direction, it will have a little less velocity in this direction with the train. Okay, all right. So this is the point here you have to remember. Okay, so you have to remember if this person is moving with respect to its frame of reference, while frame of reference also is moving, then you have to calculate relative velocity of this person with respect to the frame of reference, and then you do the rest of the thing. All right, go to the next point, next problem. Okay, so this problem is also very interesting. This is from collision. A particle of mass m with an initial velocity uy. Okay, so I have a particle, it has mass m and it is moving with a velocity u. I means along x-axis. Okay, now it collides. Okay, so a particle of mass m with an initial velocity uy collides perfectly elastically. So perfectly elastically it is colliding with a mass 3m. So 3 times. Okay, it comes and collides with this. Okay, after the collision, what happens after collision? After collision, what happens? See, initially this was at rest. Perfectly, it is colliding. See, this AM is colliding with 3M perfectly elastically when this 3M was at rest. It moves with the velocity Vj. So this guy, this small guy, okay, small mass is moving with a velocity Vj. That means it is moving after collision. It is moving in the upward direction. Upward direction. Okay, it is moving in this direction. Now, can you tell me just by guess in which direction this 3M should move? Okay, with which speed? So since this is Vj, so what you can tell from here? So what? So the answer, the question is what is Vj? Sorry, V. What is this value of V? You have to find out the value of V. So you have to guess here what should be the direction. I will be obviously applying both conservation of linear momentum, conservation of kinetic energy here because it is perfectly elastic. So in case of perfectly elastic collision, let me tell you, perfectly elastic collision. So it has two things: linear momentum conserved, and second thing is kinetic energy conserved. And obviously the total energy will be always conserved. Okay, total energy will be always conserved. So these three conservation rule can be applied here. If required, we can apply these three conservation laws. Here, see, if I have to have linear momentum conserved, see, initially there was no momentum for this capital, bigger mass, while this has. So finally, you get velocity for this small m along j direction. That means this guy should have, this 3m should have velocity at certain direction in the plane. Okay, in ij, like in terms of I and j, it should have a velocity. Why? Because see, according to this, its velocity, there is no velocity along this direction. There is no momentum, but earlier there was momentum. There should be some momentum in this direction. So look, if I draw this axis system, it has to move some direction like this. Okay, this 3m has to move in this direction with certain velocity, say say capital V. So it will have two components, one along this way, another along this way. Okay, so initially there was no momentum in the y direction, so there should not be any momentum in the y direction. Okay, so that's why this may take care of this vertical component, and this will take care of the horizontal component. So this will have, so okay, so if I write in terms of vector, this will be. So now you can actually apply law of conservation of linear momentum first. So I hope you are understanding this. So conservation law means in any direction, if you have a collision in plane, so you should have conserved quantities in both directions. Okay, conserved quantity in both directions. All right. So here, so linear momentum conserved in both direction, x direction as well as y direction. Okay, so this is minus y anyway. So I'll write in terms of vector only. Okay, so initial momentum is this. This guy was not having any velocity, so this is the initial momentum. So final momentum will be mvj, okay, plus 3m capital P vector I am writing. Okay, so look, from here I'll get the, see, m I can actually strike from everywhere. So v, this vector I'll get as u I minus vj, vj cap, actually vj cap divided by 3. Okay, or in other, like, simple way I can write this v by 3. This is u, this is v. Okay, so this is the velocity of this bigger mass. Now things will be all right. See, I can actually use the, like, I can apply the law of conservation of kinetic energy. So initial kinetic energy was half m u square, and finally it will be having half m v square along this direction, like magnitude of the velocity in the j direction. Okay, for this, okay, kinetic energy of the small mass and kinetic energy of the bigger mass, it will be v mod square. Okay, so v mod is how much? So v is q by 3 I cap minus v by 3 j cap. So v mod will give you square root of u square by 9, u square by 9 plus v square by 9. Okay, so ultimately it will be actually 1 by 3 square root of u square plus v square. This is actually the thing. So mod, so I can actually use it here again. So half m I can strike from everywhere, so let it be like this. So I have to find out actually small v, that is my m. So here it is u square, this is equal to half m v square. M I have striked out, plus 3 by 2. This is again, see, if I just square them out, actually I get 1 over 9 u square plus v square. Okay, so this is this. So 1 over 6. Look, I have got now this v 1 over 2 plus 1 over 6, 1 over 6 into v square plus 1 over 6 u square. Okay, let me check whether I have done some mistake. Hope no. Anyway, let us go. So 1 over v square. See here it will be 3 plus 1. This will be 4 by 6. That means 2 by 3. Okay, 4 by 6 means 2 by 3. 2 by 3 v square. This I can make this minus 1 by 6 u square. So this will give you 1/3 of this u square. Okay, so v square will be, so this 3 can get cancelled, so u square by 2. So this will give you v is equal to u by root 2. I hope this is the answer, u by root 2. So there will be option here, u by root 2. So C will be correct answer here. So here's the point is to be noted is that this Vj is actually the velocity of this mass, small mass, not the mass of capital, like larger mass. Okay, this is not the velocity of 3m, it is velocity of m. Actually, you had to find out what is the direction and velocity of this 3m after the collision. So you have to actually imagine this situation. Okay, all right. So we'll move on to the next problem. So this problem is again a very nice problem. You see there is a bead of mass m stays at a point this place, okay, P, on a wire bent in the shape of a parabola y is equal to 4c x square and rotating with the speed omega. The value of omega is what out of this 4 options, where you have to neglect the friction. The question is, say suppose you have a wire like this and you just rotate this about its, okay, so this, if you rotate this wire and if suppose there is a bead at this particular position and it stays while rotating, what happens here? Okay, so then at what speed you have to rotate such that, like what would be the angular speed such that this stays here? So that is the thing. So parabola, equation of parabola is given. Look what happens in this figure. So while rotating, what happens? There are multiple forces acting on this particle. I have to neglect the friction. Otherwise, also there are many forces. You look, see, while rotating at this particular position, it may actually it will actually have a normal force by this wire on this bead in this direction, and obviously there will be a force in the opposite direction. Okay, now since it is moving in a circular kind of orbit, this is moving like a circular orbit like this. Okay, so it will experience a centrifugal force, centripetal force in this direction. So centrifugal force will be in the opposite direction, having the same expression m omega square a. Okay, at this position it has this a, this radius of this circular path is a. Okay, so at the same time, see, its weight will be acting vertically downward this way. Now if I just draw a tangent at this particular position, you look this tangent. Okay, so in this this tangent makes an angle theta, say, with uh, this horizontal line along which the centrifugal force acting. Okay, so you know the centrifugal force is acting in this direction because centripetal force is acting in this direction toward the center of the circle. All right. Now mg is acting this way, so this angle is theta, means this mg is making an angle theta with this particular force, which is just exactly in the opposite direction of this. Okay, so in other words, I can say this mg is vertical like this. So if I draw a line just exactly opposite to this normal force, so this will be again theta. Okay, this angle will be theta. So mg will have a component. So actually here the forces balance. So since it is staying here, so all forces should be balanced. Mg cos of theta, which will be balanced by normal force given by the wire. Okay. Now this mg has a sin theta component along this direction. Okay, which may pull it down towards this point. Okay. So that mg sin theta will be actually balanced by the centrifugal force has a component along this direction. So m omega square a cos theta. M omega square a cos of theta according to the figure. Okay, so this will be balanced by this mg sin theta. Okay, so and see this, and obviously the centrifugal force and centripetal force, they will be balancing each other. Okay, so this is how the balance will happen, and there will be no net force, so it will stay at this particular position. So look, now the equation of this is given as y is equal to 4c x square. I hope this is the expression. Yeah, 4c x square. So let me find out tangent here, t dy dx. So at this particular position, it has x coordinate a and this has like y coordinate b. So dy by dx, so 2cx. Okay. So if I want to find out tangent at this particular position, if I put the value of ax, then I get, and x is equal to a, this will be a. Okay, so this will be 8 ca. So I have got the tangent. This tangent is again can be written as tan theta. Okay, so I'll just write it down here what I have got. So I have got tan theta, which is slope at this particular position, is 8 ca. Now look, so now from this equation I can write, say m can get cancelled, so I can write sin theta by cos theta. Cos theta, that is tan theta, is equal to omega square a by g. So this tan theta is again given by this. Okay, so this is tan theta, which is nothing but 8 ca, and that is equal to omega square a by g. Now if I simplify this, I have to find out omega, right? So from this equation, see, I can write omega is equal to 8gca, sorry, 8gc. Okay, so this a actually get cancelled from each other, so a will not be there. 8gc, okay, square root of 8gc, so which is 2 root 2 g and c. Let me see the options here. So this is the one, 2 root 2 gc. So this is actually the angular speed. Okay, so this is the answer. I hope you have understood the point here. So you have to see different forces acting on this bead, neglecting the friction. So there will be normal force, and that will be balanced by mg cos theta. Okay, there will be centrifugal force acting on that. That will be balanced actually by centripetal force, and a part of centrifugal force will be balancing the mg sin theta. So these are the points you should actually understand. All right, so go to the next problem. So this is fourth problem. So this problem says a uniform cylinder of mass m, a uniform cylinder of mass m and radius r is to be pulled over a step of height a. Look, this is a step. Okay, this is the step of height a. I have a cylinder of radius r. I have to pull it. Okay, so a uniform cylinder of mass m and radius capital R is to be pulled over a step of height a, which is less than r. So this height a is less than the radius of the cylinder. By applying a force F at its center, see, at its center the force F is applied perpendicular to the plane through which the axis of cylinder on the edge. So suppose my cylinder, actually this is a cross section, it is shown. If my cylinder is kind of, okay, so let me just tell you. Suppose my cylinder is like this, you have to pull it like this. Okay, this is the axis and this is the force applied. So this is what it is saying. Axis means it will be rotating. Okay, rotating with respect to this axis of the cylinder. Okay, so axis of the cylinder you can see this way. Okay, this. All right. Now what is the minimum value of force F required for this? So ultimately the problem is that you are just pulling a cylinder over a step. Okay, and step has height a and this cylinder has radius capital R, which is much greater than a. So what is the normal force you have to apply at the center of this cylinder such that, like force normal to the axis, such that you can actually take it to here. So for that, you know, the torque applied here at this particular position P, torque here must be greater than, so torque due to this force must be greater or equals to, the torque at the center, sorry, torque at this particular position due to the weight, mg weight, torque due to weight. I'll write w, tau w. So the torque at this position due to the weight and torque due to this force at this point, I have to calculate and then equate. So that will be actually minimum force. So to get minimum force, what I have to do, look, this is the replica figure here. Okay, this is A and this is R. So I get tau F, torque due to the force at this particular position P is F into perpendicular distance R. Okay, that is fine. Now this is the weight acting this way. So I have to get this normal distance. Okay, this distance x. So you get torque due to this weight is mg into x. So this torque has to be greater than or equal to this. So for the minimum force, I can write Tf is equal to Tw. Okay, so what is Tf? Okay, so Tf is Fr, because this is 90 degrees, so F r sin theta will be 90 degree, and this this x, this is also 90 degree. So this perpendicular distance x, I have to find out mgx. But what is this x? Let us find out. So to find out this x, you look here, up to this is it is actually r radius again. See, up to this one, this is height a. So what is this? This is actually r minus x. Okay, this is r minus a. Up to this, it is a. Okay, I'll just redo this so that you can understand it. I have to find out x here. Okay, so I have this triangle. See this. This is r. Okay, so this particular height is r minus a, because see, look, this is up to here, this is a, and this the total is r. So what is this? This is r minus a. This is r minus a, this guy. Okay, so now I have to find out x. So Pythagoras rule I can apply. So x will be square root of r square minus r minus a whole square. Okay, so this I'll write. Let me then do it here. So if r is equal to mg, in place of x I'll write square root of r square minus r minus a whole square. So what will be the force? F will be is equal to mg by r square root of this r square minus r minus a whole square. So this r I'll just multiply inside. Let me see how it comes. So this has to be squared, and this will be r minus a by r whole square. Okay, this is actually the minimum force. Okay, let me check the options. Yes, so this is the answer. So m will be capital. Okay, so this is the answer. So the point here is that you have to find out the torque about this particular point. Okay, torque about this particular point due to the force and due to the weight. Okay, due to the weight, and that you have to equate to get the minimum force. Excuse me. A cylindrical vessel containing a liquid. So this is the last problem for this session. A cylindrical vessel containing a liquid is rotated. So you can see this cylindrical vessel. It is rotated about its axis so that liquid rises at its height as shown in the figure. You look, this is actually, see, if I just draw it here, suppose this is a container. Earlier liquid level was like this when it was at rest. Okay, but when you start this container rotating with certain angular velocity, then what will happen? You look that this you might have experienced rotating a balti. Okay, bucket, rotating a bucket or any kind of container. If you rotate, if you are able to rotate, then you will be seeing that there will be rise of liquid at the ends like this. So this is what it is here. So but okay, so the radius of the vessel is given. See, radius of vessel is 5 centimeter, that is given here, and angular speed of rotation is given here, omega. The difference in height of liquid at the center of the vessel and at the side. See, side is this one. Now this is height h, and at this position height is actually, if I take this as a reference, if I take this as a reference, so this height is 0, say. So you have to actually find out the increase in height, okay, with respect to this reference. This is actually the question. So difference in the height of the liquid at the center of the vessel at the side will be. See, you might be thinking, see why this liquid is rising, why liquid rises on upon rotating, okay, why liquid rises on rotating. Okay, so this might be a question, right? See, if I take this, let me just keep the situation when there was no rotation. Okay, there was no rotation. Then the liquid surface will be looking something like this. Okay, so this has horizontal position. Okay, on the top surface, this is suppose open surface. So the pressure is here, how much? Atmospheric pressure. Okay, so now when, so everywhere it will be atmospheric pressure, right? At this position, this position, this position on the top surface. Okay, so everywhere if I say this position is A, this position is A, and this position is B, so everywhere pressure will be the same. PA and PB will be the same. Okay, because it is actually, see, if you see this is the top surface, this will be actually atmospheric pressure. Understand, it will be atmospheric pressure. But what happens when it is rotated with angular velocity? Then see, according to Bernoulli's principle, according to Bernoulli's principle, what happens? So this pressure energy plus, sorry, kinetic energy per unit volume, pressure energy per unit volume, kinetic energy per unit volume is half rho v square, and the potential energy, okay, potential energy all together will be constant. Okay, all together this will be constant. So when it is horizontal surface, this potential energy part will be not there because H is 0. So finally what is happening at for horizontal surface, if you rotate at the horizontal surface, half rho v square plus the pressure will be constant, isn't it? This should be constant. Okay, this should be constant. P, pressure plus the kinetic energy at each point should be constant. But look now, when it is rotated, there will be speed. See, if I rotate something, okay, rotate something by about this axis. See, point or near the axis will have lesser kinetic energy, at least linear kinetic energy. I'm saying half of this question. This V, linear speed near the axis will be less than the perimeter. Okay, perimeter of this, or at the edge. Okay, at the edge, so the speed will be greater because V is equal to R into omega. Omega is the speed which is equal for each and every particle. Okay, each and every particle. But the particle at this particular position at the edge, it has greater radius, right? Greater radius, so it will have greater velocity, linear velocity. But this product has to be constant. So how is it possible that it will be constant when the speed is increasing at the edge? So speed is increasing at the edge. That means what has to be happening here such that the whole quantity should be constant. So pressure should decrease. I'll just come again here. So I have P plus half rho V square, but at the edge, let me draw it here. At the edge, at this position is A, this position is B. At the edge, what is happening? If my axis of rotation goes like this, so at this position speed is less, so the product will be, so this should be constant. So pressure must be maximum here or greater here. Speed is 0, right? Speed is 0 here. So speed is maximum here. So pressure should decrease so that this quantity, total quantity should be constant. So at this particular position, actually P will be decreasing, okay, and V will be increasing at this particular position at the ends. But see, at the same time, see, both are actually exposed. Both ends are exposed to the atmosphere, right? Both are actually exposed to the atmosphere, so the pressure should be same at the same time, isn't it? Pressure should be same at the same time. So to make the pressure same, so this is happening. See, this height has to rise at the edge such that the pressure at this PB plus H rho G must be equal to PA. Okay, so this should happen. Okay, so this is why there will be rise at the edge. Okay, rise of liquid at the edge. Now if I apply Bernoulli's theorem, okay, so I can actually write pressure energy plus half rho v square, so pressure energy at A, half rho v a square is equal to PB plus half rho VB square. Okay, B is this point. I'm sorry, this is actually, yes. Now look what will happen. PA minus PB. This is here. And so this VA on the axis, VA, this point is on the axis, and on the axis R is 0, so linear velocity 0. So VA will be 0, this particular term will be 0, and I will have half rho VB square here, half rho VB square, and VB square can be found out from R omega. Okay, R means I have to see the radius is given. Okay, radius is given, and see this particular term I have got H rho G, right? H rho G, H rho G. This is equal to half rho VB square. So VB square, I'll just put the value omega square R square, and this rho I can strike them out. So I will get H is equal to H, that is the height is equal to omega square R square divided by 2G. All right. So this will be actually the rise in height with respect to this point A. All right. So I hope this is not making you confused. So here if you put the value 5 centimeter, so height you have to find out in centimeter. Okay, so 5 centimeter is radius given, omega square is omega square itself, and this is 2g. So you will get height as 25 omega square by 2g. So there will be options here. So 25 omega square by 2g. So option B will be the correct answer for this question. Okay, so with this I'll stop it here for today. So thank you for your patience. Bye for today.